Good day, everyone. Today, we're diving into the April 2026 Telegram blockade upgrade incident. We'll analyze how AI-powered Deep Packet Inspection, or DPI, targeted Telegram MTProto proxies, specifically identifying that obfuscation-free MTProto proxies are no longer viable. We'll also share two community-verified solutions to keep your Telegram connection stable. This is a joint effort from our Network Security Privacy Analysis Technical Research team, focusing on encrypted traffic and network security research. The incident we're discussing took place across Russia on April 1, 2026. Let's start with what we'll cover today. First, we'll set the stage with an introduction to the familiar disconnection issues many faced, but with an unfamiliar AI-powered enemy behind them. Next, we'll break down the technical core of the April 2026 blockade, explaining how AI-driven DPI spots proxy traffic through TLS stack and TCP behavioral fingerprints. Then, we'll walk through two community countermeasures. First, the MTG 2.2.8 fingerprint fix, including its technical updates that evade AI detection. Second, the dual-layer proxy architecture that uses domestic MTProto plus VLESS and reality tunneling to keep traffic off international routes. Finally, we'll give you a guide to choosing between these solutions and share our conclusions on what's ahead. Let's begin with our introduction, a familiar loss of connection, but an unfamiliar enemy. On April 1, 2026, users across Russia faced massive failures with Telegram MTProto proxies. This wasn't just slow or laggy service connections couldn't even complete a handshake, leaving users completely locked out. Here's the paradox: users had the same VPS, and while MTProto on port 443 failed entirely, VLESS Reality on that exact same port worked perfectly. That told us this wasn't a simple IP ban. All the traditional workarounds stopped working too, changing IP addresses, switching ports, replacing hosting providers, none of it helped. The enemy had evolved beyond static blocking. The real culprit? A full upgrade to AI-based protocol fingerprinting. Instead of just blocking proxy servers, internet operators started analyzing client-side TLS behavior patterns to recognize proxy traffic. For unprotected MTProto proxies, network connection failure has become the new normal. Before this incident, proxy nodes could last for weeks, but after April 2026, their lifespan dropped to less than 48 hours. Now, let's look at the technical essence of this blockade, starting with the limitations of traditional DPI. Traditional DPI uses three main mechanisms, each with clear limits. First, IP and port blacklists. These collect known public MTProto proxy server IPs and ports to block them directly at the firewall. It works for static nodes, but fails against dynamic or private IPs, as it only targets server infrastructure. Second, SNI whitelists. These only allow TLS handshakes that include approved domain names in the server name indication field, blocking unrecognized domains to restrict unauthorized proxy access. This targets the domain handshake process. Third, static packet signatures. These scan raw packet payloads for fixed protocol fingerprints, like the MTProto default magic byte value OXCF, to instantly flag unobfuscated handshakes, targeting the protocol payload. But there's a loophole: fake TLS obfuscation, using secrets prefixed with EE, wraps MTProto traffic inside a standard TLS 1.3 client hello. Since it mimics legitimate HTTPS traffic perfectly, traditional DPI can't find static signatures, can't block the whitelisted SNI, and has no choice but to let the traffic pass. Now, let's move to how AI-powered DPI sees through this obfuscation, marking the evolution of deep packet inspection. Let's compare traditional DPI with AI-enhanced DPI. Traditional DPI focuses on static signatures like IP, port, and magic bytes, is completely blind to fake TLS obfuscation, and passively blocks proxy server IPs. AI-enhanced DPI, on the other hand, focuses on TLS handshake fingerprints and behavior, can distinguish Telegram traffic from standard browser traffic, and actively injects client-side RSD packets to disrupt connections. There are 4 core AI fingerprint targets it uses. First, Cipher Suite's Telegram prioritizes less common suites like AES 256 GCM over browser defaults. Second, Grease Values Telegram uses fixed or predictable patterns instead of the true randomness standard browsers use. Third, extension order. The specific sequence of TLS extensions in Telegram traffic differs from that of Chrome or Firefox. Fourth, TCP behavior. It analyzes unencrypted features like keep alive intervals and window sizes. The core paradigm shift here is that AI no longer cares about what clothes your traffic wears, meaning encryption obfuscation. It watches how your traffic walks, focusing on behavioral fingerprints. Let's continue exploring the technical essence, how the blockade shifted from blocking servers to disconnecting clients with an active client disconnection mechanism. Here's how the 2026 DPI upgrade actively targets and terminates client connections. First, TLS fingerprint identification. AI-powered DPI analyzes the client's TLS handshake, including cipher suites, grease values, and extension order, to instantly detect Telegram's unique TLS stack. Second, forged TCP RSD injection. Once it identifies the traffic, the DPI system actively injects forged TCP reset packets to both the client and the proxy server during the handshake phase. Third, immediate connection drop. The connection is severed right away. The probability of successful termination follows this formula. P drop is approximately equal to 1 minus 1 minus PRSD raised to the power of n, leaving proxy nodes completely unusable. This shift dropped node lifespan from weeks to less than 48 hours, and importantly, the attack now targets the client side with active RSD injection. Now, let's look at our first countermeasure, the MTG 2.2.8 project, a fingerprint-level defense. MTG is a highly focused open-source MTProto proxy implementation for Telegram, and it's currently the most actively maintained open-source tool built specifically for countering DPI. Its anti-DPI design philosophy is built from the ground up to evade deep packet inspection using fake TLS, random SNI generation, and multiple obfuscation modes that mimic legitimate HTTPS traffic. Version 2.2.8 was an emergency response, released within 1 week after the April 2026 blockade, specifically addressing the fingerprint vulnerabilities exploited by AI-powered DPI systems. Its key updates include dynamic grease values to eliminate fixed cipher suite patterns that AI models memorize, a browser-grade TLS stack that mimics Chrome and Firefox handshake fingerprints exactly, and TCP behavioral hardening with BBR congestion control plus timeout randomization. For context, the MTG GitHub repository has over 2.8 thousand stars, runs on the MIT license, and its latest release is version 2.2.8. Let's dive deeper into the core updates in MTG 2.2.8, all focused on fingerprint-level security enhancements. First, dynamic random grease values. The server hello no longer sends fixed grease values. Instead, it uses dynamic random generation to counter DPI rules based on static grease patterns, directly addressing fixed grease detection. Second, browser-aligned cipher suites. It removes uncommon cipher suites, keeping only combinations that are common in browsers, eliminating heuristic detection based on anomalies in cipher whitelists. Third, dynamic certificate noise. It fine-tunes certificate chain order and extension fields for each handshake, preventing AI from memorizing static certificate features and stopping static certificate fingerprinting. Fourth, custom handshake timeout. A configurable handshake timeout replaces the fixed 60-second default, eliminating behavioral analysis based on predictable timeout patterns. Fifth, TCP BBR congestion control. It enables the BBR algorithm with optimized user timeout settings, normalizing retransmission patterns that previously revealed weak network behaviors and countering TCP pattern analysis. Sixth, TCP not sent low at buffer. It adjusts the send buffer low watermark to reduce small packet aggregation delays, eliminating packet size pattern fingerprints from buffer behavior. With all these updates, MTG 2.2.8 closes all major fingerprint vulnerabilities exploited by AI-powered DPI systems, achieving complete JA3S fingerprint parity with Chrome 132. Now, let's evaluate the effectiveness of MTG 2.2.8 based on performance and community validation. First, verified TLS handshake identity. The JA3S fingerprint matches 100% with Chrome 132. That means the client-side TLS stack is fully aligned with standard Chrome browser traffic, successfully bypassing heuristic DPI rules by matching cipher suite orders and extension patterns. Second, active noise calibration. It uses dynamic feature randomization, meaning there are zero static signatures. The standard deviation of noise is greater than the detection threshold, so it fine-tunes certificate chain order and extension fields during each handshake, preventing AI-based DPI models from memorizing static certificate features and blocking the connection. Third, stable node survival rate. Self-hosted private nodes have achieved continuous uptime of 30 or more days. By bypassing active DPI client disconnect attacks, MTG 2.2.8 ensures long-term availability for personal use. Moving to our second countermeasure, the core insight behind the dual-layer architecture, focusing on geographic DPI bypass and routing logic. There's a strategic gateway vulnerability to exploit. Russia's TSU DPI equipment is almost exclusively deployed at international internet exchange points, like MSKIX. This means domestic intra-Russia traffic completely bypasses these deep inspection checkpoints. The probability of DPI inspection for domestic traffic approaches 0, while the probability for traffic passing through gateway points approaches 1. This is border-only DPI filtering. Deep packet inspection is highly concentrated at the nation's digital borders, leaving internal routing unmonitored. That's the foundation of the dual-layer architecture. By splitting the proxy into a domestic hop and an encrypted international tunnel, MTProto's signatures never cross the border. Traffic passing through gateway points faces active inspection, but internal domestic traffic is fully bypassed. Now, let's look at the design of the dual-layer architecture using two-hop routing and traffic obfuscation. The flow starts with the Telegram client at the local user's end. The first hop is an intra-Russia domestic VPS running RU MTProto. Since this traffic stays within the domestic network, it completely avoids passing through international gateway TSU inspection points like MSKIX, so the probability of DPI detection is approximately 0, fully bypassing deep TSU AI DPI inspection. The second hop uses a VLESS Reality encrypted tunnel to an overseas egress server. All cross-border MTProto traffic is fully encapsulated in this tunnel, and the outer layer mimics the TLS handshake of a legitimate public website, making it completely indistinguishable from normal browser traffic, evading AI fingerprint identification at the international gateway with a TLS fingerprint identical to Chrome 132. Finally, the traffic is decrypted to direct TLS and sent to the official Telegram server destination. Let's go over the advantages and deployment recommendations for the dual-layer architecture. It has 3 core advantages. First, no MTProto feature exposure. Cross-border links use VLESS Reality tunnel encapsulation, so DPI can't parse the inner MTProto payload through the fully encrypted outer tunnel, making traffic identification impossible. Second, extended node lifetime. Public shared nodes run stably for an average of over 6 months, far exceeding the 48-hour survival of direct connection MTProto proxies. Third, native client compatibility. No third-party proxy clients are needed. Users just add the domestic MTProto address in official Telegram settings to use the service normally. Now, deployment recommendations. First, server selection. Deploy the intra-Russia MTProto on mainstream civilian cloud platforms that offer regular domestic services. Avoid small niche VPS vendors that are subject to frequent audits. Second, reality certificate configuration. Select high-traffic mainstream domain names as reference reality certificates, eliminating TLS fingerprint differences and ensuring fully browser-like behavior. Third, connection limit setting. Limit the maximum simultaneous connections per domestic MTProto instance to below 200, preventing abnormal aggregated traffic characteristics that could trigger detection. A pro tip, monitor traffic patterns regularly and rotate reality certificates every 3 to 6 months for optimal stealth. Now, let's walk through a solution selection guide with tailored strategies for different deployment scenarios. First, option A for personal use, MTG 2.2.8 deployment. This is best for individual users who want a quick, cost-effective, straightforward setup to restore personal Telegram access. It's ultra-low cost, requiring only a single, inexpensive overseas VPS, no secondary routing or domestic relay servers needed. It takes just 10 minutes to set up with a simple Docker-based installation and minimal configuration, perfect for non-technical users. It uses client-level obfuscation to emulate standard browser TLS fingerprints from Chrome 132, evading heuristic DPI detection. The difficulty level is very easy, with an estimated monthly cost of $2 to $5. Option B is for team or public use, the dual-layer architecture. This is designed for small teams, families, or public shared node operators who need maximum anti-blocking resilience and scale. It offers ultimate DPI immunity, encapsulating MTProto inside VLESS Reality so cross-border traffic looks like legitimate web browsing. It provides long-term stability, with an average node lifespan exceeding 6 months, drastically reducing the overhead of constant IP or port migration. It's optimized for multi-user use, supporting up to 200 concurrent users per instance without triggering ISP traffic anomaly alerts. The difficulty level is moderate, with an estimated monthly cost of $5 to $10. Let's wrap up with our final insights and future directions. First, key takeaways. The 2026 AI DPI upgrade has rendered outdated, unoptimized free public MTProto proxies obsolete, but that doesn't mean MTProto technology is dead. Stable Telegram connectivity is still achievable through 2 proven approaches. The first is fingerprint optimization. MTG 2.2.8 eliminates TLS stack and TCP behavior fingerprints, making proxy traffic indistinguishable from normal browser traffic. The second is route-based evasion. The dual-layer architecture keeps MTProto traffic off international routes where AI DPI is deployed, using domestic MTProto plus VLESS and reality tunneling. Looking ahead, anti-DPI iteration will focus on eliminating behavioral differences between proxy traffic and normal browsing to match AI's continuous evolution. The future of resilient proxy infrastructure lies in the fusion of security measures and connectivity solutions. Now, we'll open the floor for a Q&A and technical discussion. Thank you all for your time. Let's work together to build a more resilient and open network environment. We're the security OPS team with the Network Freedom Initiative, focused on global collaboration. You can reach us at research@anti-block.net, find our open source work at github.com/9seconds/mtg, and our technical focus areas include MTProto obfuscation, AI DPI countermeasures, and multi-hop tunnels. We invite you to join the discussion and share your experience. This work is copyrighted to the 2026 Secure Connection Initiative.